I want to show you how to use the integrated logic analyzer as a virtual logic analyzer that you can actually upload as on your FPGA along with your circuit, and it will effectively be your logic analyzer as if you have a bench logic analyzer and you can use it. Of course, it's limited, but it will serve a purpose for certain projects. This integrated logic analyzer is an intellectual property that is designed by Xilinx, and you can actually see it's embedded already in your Vivado. You can read the documentation in here to get the product guide, but what I want to do is I'll jump to Vivado and just show you how to use it. So we're going to go to Vivado in here and see it. All right. Okay, so what I have in here is basically I have a circuit that has an M as an input, N as an input, of course clock and reset as inputs, and it generates a square wave, as you can see at the last row. So M and N defines, I believe M defines for how long it should be in the on position, and N is how long it should be in the off position or the 0 position. So at the beginning, you're going to see that M and N is set to 1. That means it's 100 nanosecond in the on, and you can see this one is 100 to 200. And it's also because the N is at 1, that means it's going to stay for 100. That means this one here is 300 nanosecond in the off position. Of course, if you change these numbers a little bit, for example, let's see it here, you can see that M is 4 while N is 1. 4 indicates that it's going to be on for 400 nanoseconds. So if you stop in here, which is 1 million, that is 1,400,000 or 1,400, sorry. Okay, so 1,000 to 1,400, which is 400 nanosecond, exactly what I expected. And of course, because it's 1, N, the value of N is 1, it's going to stay for 100 nanosecond. And you get the idea. All right, so how do we use the ILA? Well, you're gonna have to go to your IP catalog in here and look for ILA, okay, which is Integrated Logic Analyzer. You double click on it, and we get to see you get to see that wizard to set it up. However, you can definitely use this, but I'm gonna just show you an easier way to use the Integrated Logic Analyzer. And the way we're gonna be doing it is we're gonna go to the synthesis, we're gonna open synthesis design, and then we're gonna go to setup debug. Okay, within that setup debug, what you will see is another wizard, and we're gonna have to add these probes for the signals we care about. For example, we care about M, okay, because I care about the input M in here, so we're gonna look for it. It will return a bunch of things in here. We're gonna select the first one, which is an input buffer. That's what we care about, okay, which is a 4-bit input buffer. That's exactly what we're looking for. Okay, and then next what we're going to be doing is we're going to add another one in here, and now we're going to do star N so that it looks for anything that has the letter N in it. I don't care about the FF and N and blah blah blah. It's part of my design. What I care about is the input buffer. That's what we're going to be adding. Okay, and then we're going to add the clock, for example. I called it clock. You might have called it a little bit differently. So we have a couple of buffers. I will just use the input buffer in here. That's okay. And before we click next, we're going to add the last one, which is actually what we care about, which is the square wave. Okay, so we add the square wave in here. You would look at it as output buffer, and that's exactly what we're looking for. So these are data and trigger. That's what they're set up to be. Technically, the trigger should be the clock only, so I'm just going to put it to trigger. But I believe if you put it this way, you won't be able to see its signal, but that's fine. I mean, I don't need to see the clock itself. Okay, so we're going to go through this here. And I move the M and N and square. They're not trigger. The logic analyzer is not going to be triggered by these signals. It's just going to display it. So we're going to just use the probe type as data. Then we click next. And in next here, I believe the sample data depth should be fine. I tested it with a bunch of numbers. I believe I tested it with that. I can probably run it with 1024. That's fine. I'll just add the input pipe stage to 5. I'll check these two links here, or these two checkboxes here. We click next. And then here, what we need to do is actually click finish, and we wait a little bit. So now it's finished. What we're going to have to do is just go and say generate the bit stream. So in here, I'm being asked, let me show you that window here. Okay, so I'm being asked if I want to actually save the project. I will save the project. Okay, and here I'm being asked if the constraint file has changed, whether I want to have it in a new file. All I'm going to do is just select the existing file, and I'm just going to add to it. So you're going to see at the very end of the synthesis, it will add to my constraint file a little bit. So we're going to click OK in here, and that's okay. We're going to click yes, and then we're going to run it, and it'll take a few minutes. It's basically I'm running the synthesis again and the implementation again and everything. Okay. If you don't see the M and N for some reason, when you clicked on the setup debug during the wizard, try to run at least a synthesis and then run it again. Probably you need to do that in order for the wizard to see these signals, okay? So we're gonna click OK. So while it's running the bit stream generation, I wanted to show you I'm inside now my XDC file. And this is just a generic XDC file that we've been using, the constraint file. But what I want to do is I want to scroll it to the very end, and I want to show you that this ILA has added a few things in here. You don't need to understand everything in it, but it's basically you can read it on your own and figure it out. But you just need to know that these windows that we went through it, they just basically asked us if we want to save it in a new file or just add it to it. It just appended it at the very end of the file. So now that it's done, what I can do is I can just basically open the hardware manager in here, open the target, connect my FPGA to it, and now I can definitely copy the file or upload the file, the bit file into my FPGA by programming the device. What I want you to see in here is now I have another file in here, which are the debug probes, and this contains information about the MN and all the other fun stuff we did. So we're going to program the FPGA, and what you get to see is the following. You're going to see a window now appearing in here, similar to the simulation window. Okay, it's extremely similar, and it's doing pretty much the same exact thing, but it's actually running from the FPGA. Okay, so I'll show you, here's the FPGA now, and you can see nothing is appearing on it. Like I have these slide switches connected to the M and the N. The first 4 I believe are M, the second 4 are the N. I will just set them up now to be exactly 1 and 1. That's the easiest thing. Okay, 1, 2, 3, and 4, and this is 1, and we get to see it. So now if you see this waveform in here, you're going to see that I have that particular signal, and it should be 100 nanosecond on, 100 nanoseconds off, and this is what I see in here. Very, very close to 100, not exactly 100. Probably if I played around with a waveform generator or something like that, you're going to see it. And just to test it, you're going to see that my off and on are actually changing whenever I change the switches in here. But anyway, we don't, like most of us do not have this particular fun wave generator in here. So what I'll do is I'll just disconnect it, and you can see that I have outputted that signal on the JA. This is why I was able to see it. Do not forget, if you have that particular waveform, do not forget to connect the ground as well. Okay. So now what I want to show you is what's happening on the window in here, the simulation window, or it's not the simulation, it's actually the ILA, the integrated logic analyzer window. So I do have the N buffer, the M buffer, and the square wave, and I'll be able to see everything in here. So you're going to have to click this one here. It's a little bit on the slower side, that's okay. All right, you're going to click on that, and then for example, if you wanted to run continuously, you run that, but if you just wanted to capture just one with one trigger, you're going to click on here, and what you're going to see, you'll wait a few seconds, and you get this window. So let's take a look at this window. This basic window, okay, it went away. Okay, this basic window, what's it doing? I think I clicked on that. Okay, so let me just do this here. I'm gonna stop it. Okay, so I stopped it now just so that we get to see it. So you can see the waveform generator is actually generating a 1 and 0, and M has 1 and N has 1. And you can definitely zoom in and just see it even more, and you can look at it exactly like what we did in the simulator. So if we jump from here to here, we're going to see 174 all the way to 184, and the difference is 10, and you probably would be thinking, well, shouldn't it be 100 nanosecond? And the answer is yes, it's still 100 nanosecond, but the clock is operational at 10 nanosecond, and this particular window is triggered every 10 nanosecond. So everything you see in here, it's actually not in the 10 nanosecond, it's actually between here and here. This is actually every move you see is actually 10 nanoseconds. So from here to here, the difference is actually 10. You multiply by 10 and you get the exact nanosecond. So if I want to basically, I know that this should be 100 in the off, so 100, but I'm going to divide that 100 by 10. That means I'm going to basically stop at 194, and that's exactly what I see. So you get a logic analyzer in here. And I'm just going to show you that you can definitely change the on and off, for example, or the switches. So I'm going to change these switches. So the button I switch in here is actually going to continuously do it, and I'm within my current zoom, which is fine. It's not going to zoom me out. Okay, so I'm just basically going to increase these in here. I'm going to basically put maybe 2 on the M, okay, and the M is actually the second one, or 3 actually, because it's a 1-1, okay, and I should see something a little bit longer in the on and a little bit like off. In the off, it's going to be shorter. So you can stop it here if you want to actually, if you do care about just checking every value. We're going to stop it again. Okay, this stops it. It's a little bit on the slower side, so you got to be patient. So from here, from 175 all the way to 205, you get to see it should be 330 basically, which is times 10, it's 300 nanosecond. This is still at the 100 nanosecond divided by 10, that should be 215. That's correct, okay? And I can basically see a little bit more, and you get the idea. So you can basically go 700, for example, and you get the other signals. And of course, if you actually just run it continuously and you just basically zoom out completely, and you get to see the whole signal here, which is 7.7. And you can basically do that. I'm gonna make it a little bit longer in the on than the off, and that's exactly what happened in here because I put F, which is 15 in the M, and 7, it's gonna be in the on. So you get the idea. Now you have an integrated logic analyzer, and this logic analyzer is actually running on your FPGA. It's actually not simulated. This is actually real time, as you can see in here.